Bismillahirrahmanirrahim. In this chapter, discussion on virtual memory continues and we'll discuss some more topics related to virtual memory. Since virtual memory is quite an intensive topic, so I have divided it in two chapters. In previous chapter, we have seen different techniques of virtual memory, and in this chapter again we would discuss some more techniques related to virtual memory. What all we are going to discuss? Let's see the outline for this chapter. This is all what we are going to discuss in this chapter. We will first recap the topics we have already discussed in order to develop your background. Then the concepts in virtual memory will be discussed that include demand paging, page fault, different page replacement techniques or algorithms, the address translation using direct and associative mapping, and at the end, pre-paging concept will be discussed. Before moving ahead to discuss different concepts related to virtual memory, we first need to develop your background. What is virtual memory? As we said in previous chapter, that virtual memory is physically part of secondary storage, but it acts as second RAM in order to provide a logical address space for the processes. Processes need to be loaded to actual RAM for execution, and execution does not take place from virtual memory. Virtual memory only provides a boost to actual RAM in order to enhance its storage capacity. RAM is known as physical memory, while virtual memory is known as logical memory. Since virtual memory is part of secondary storage, hence it has larger storage space as compared to physical memory, which is RAM. We already have seen the memory hierarchy in previous chapters. Virtual memory is also shared among different processes, and more than one process reside in virtual memory. Virtual memory can be implemented using two techniques, which are demand paging and demand segmentation. We already have discussed paging and segmentation in previous chapter. So, demand paging and demand segmentation techniques both are applied on pages and segments respectively. They both work similarly, so I will be discussing one of them and the other works the same. This figure shows the difference in the capacity of both physical and logical memory. Since virtual memory is part of secondary storage, so its storage capacity is higher than the physical memory. Pages or segments are mapped from virtual to physical address, and from physical address they may again swap out to virtual storage, which resides on secondary memory. So, virtual memory, this is physically part of your secondary storage, and pages are swapped out from physical memory to secondary memory. I hope you have developed your background. Next, now we will be moving towards demand paging. And let's see what is demand paging. What is demand paging? As the name indicates, demanding a page, that means a page is loaded in RAM only when it is needed. There are different benefits of demand paging, such as less I/O would be required by pages, as by large those pages will be loaded that are CPU bound than I/O bound, as demand goes mainly for CPU bound processes. Second benefit is less memory is required if only needed processes will be loaded in main memory. Instead of wasting memory with blocked or unused pages, it is better to use memory efficiently by loading only needed pages or segments. Another benefit is faster response, and it is due to the fact that CPU will be more busy in executing instructions within the pages or segments, and quick response will be generated from CPU. Next benefit for demand paging is that more users will be supported, as pages of more than one processes of different users will be allowed to be stored in RAM. How demand paging is implemented? Whenever a page is needed, it is referred or referenced. Now there are two situations. If the reference is invalid, as you can see, first point, if the reference is invalid, that means the page is not present in the main memory. So that reference is aborted. While the second situation may be, as you can see, if the reference is valid, that means the page is not present in main memory and is located in logical memory. So then that page is loaded in RAM. Here, the swapping mechanism is shown. The pages which are blocked are swapped out of main memory to virtual memory, while the required or demanded pages are swapped in back to main memory. So swapping mechanism is shown in this diagram. We already had discussed valid, invalid bits in previous chapter. Every entry of page table has valid, invalid bit associated with it. Valid is represented as 1. That means specific page is present in main memory. While invalid bit is represented as 0. That means specific page is not present in main memory. Initially, all entries for a process in page table are set to 0. When address translation happens, and if a reference page has 0 bit with it, so page fault occurs. Now, what is a page fault? Next topic of discussion is page fault. So let's see what is a page fault. If a reference to a page is traced to 0 in page table, so page fault occurs, which means the required page is not present in memory. Page fault acts as a trap for operating system because operating system leaves everything and tries to search out the required page in secondary memory. Searching secondary storage takes a lot of time as it has higher storage capacity. Now for 0 bit, operating system has to be very careful to identify if the frame is invalid or the page is just not in main memory. After confirming it, if the reference is invalid, the instruction referring that page is aborted. But if it is just not present in main memory, so operating system would load that page in main memory. For loading a page in memory, operating system needs to first create space for it in RAM. Operating system first has to find a free frame. Then swap in the required page in that frame. Once the page is moved in the particular frame, so the page table entry for respective page will be updated. Initially, its validation bit was 0 and now it has to be set to 1. Once page table entries are updated, then the instruction referring to this page is restarted. This is how page fault is handled. The steps that we have discussed in previous slides are represented diagrammatically here. Here you can see how page fault is handled is represented stepwise. The page that is being executed on CPU requests another page or an instruction located on some other page. So here you can see in step 1, a running page references an instruction which is located on another page. So operating system first looks for that page in that respective process page table to see if the required page or the referenced page is located in RAM or not. So how that is to be found? Operating system looks for the protection bit here. The protection bit of the referenced page within the page table is observed to see if it is a valid page or an invalid page. If this protection bit is set to 0 or I, that shows that specific page is not yet loaded in RAM. And if this protection bit is V, that means valid, or 1, which is generally represented as 0 or 1. So if it is 1, that means the specific page is already present in RAM. So now since we are discussing page fault, so that means the required or referenced page is not loaded in RAM and its protection bit is 0 or I. So this would result in a page trap for operating system. Here you can see in step 2. So an invalid page reference results in page trap or a trap for operating system. A trap means operating system leaves everything and starts looking or searching for the required page. Now in step 3, here you can see, since the page is not loaded in RAM, that means it has to be located somewhere on secondary storage. So operating system searches the specified or the required or the referenced page both on virtual memory and secondary storage. Once the page is located on secondary storage, then operating system first has to find some space for that page in main memory. Here you can see. So in physical memory or main memory, operating system has to first find some free frame for the incoming page. If there is a free frame, operating system loads that required page from secondary storage to physical storage on that free frame, as you can see in step 4. But this is only if the free frame is available. And if there is no free frame, then what has to be done? Operating system then swaps out one of the pages from main memory to secondary memory and loads the page, the required page, at its place, which we call as page replacement. We'll be discussing different page replacement techniques in the coming lectures. But for now, for this diagram, we suppose that operating system finds some free frame in main memory. So the required or the reference page is loaded in that free frame. Then, now, since the page has been loaded in RAM, but before starting the execution of that reference page, operating system first has to reset its entry. The required page table entry is reset in the page table. So here you can see in step 5, since every page within the process has an entry in page table. If the page is loaded in RAM or if the page is present in RAM, its protection bit is set to 1, and if it is not present in RAM, protection bit is set to 0. So once the page has been loaded in RAM, earlier its protection bit was 0 or I, but now since it has been loaded in RAM, so its protection bit need to be reset from 0 or from I to V or from 0 to 1 in order to show that the page is present in RAM. And whenever in future the request for this page is made, operating system, instead of searching it in secondary storage, could get the page from the main memory. So page table helps operating system in locating the specific page. So after resetting the page table entry for that incoming page, in step 6 you can see the page that has referenced this new page gets restarted, or the specific instruction within the page that has requested this new page gets restarted. Not the complete page is restarted, only the specific instruction that has referenced this new page gets restarted so that the instructions within the new page can be timely executed. So this is how page fault is handled by operating system. It is a time-consuming task for operating system since it is a trap for operating system. How it is done? The steps are now clear to you. The running process makes a reference to some page. An operating system looks for the page table to find or to locate the location of the reference page. If the protection bit of the reference page is 0, that means this specific page is not present in RAM. So operating system has to then stop everything and start searching for that page on secondary storage. Once the page has been found on secondary storage, now is the time that this required page should be loaded in RAM. But before that, operating system has to create a space or find a free frame for that page in main memory. If there is a free frame, that required page is loaded in that free frame. But if there is no free frame, then some other page has to be swapped out in order to create space for this new page. Once the page is loaded in RAM, page table entry associated with this page gets updated. Earlier, its protection bit was 0. Now, after loading it in RAM, its protection bit is reset to 1. And the instruction that has referenced this page gets restarted in order to execute instructions within this referenced page. So this is the complete mechanism how operating system manages page fault. In previous slide, we have seen page fault, and we had observed an ideal situation. That means there were free frames available in RAM or physical memory. But now what happens if there is no free frame in physical memory? Now this is the time that operating system has to initiate page replacement. Page replacement means that operating system has to swap out one of the pages located within RAM to secondary storage and swap in the required page at its place. So the page that is swapped out is generally the one which is blocked. The blocking state, you already know, is the one in which the page is not running on CPU, rather it is waiting for some event, for some user interaction, for some hardware resource, or for some any other event. The page is blocked. It is not working. So generally or commonly, a blocked page is swapped out to secondary storage in order to create a free frame for the requested page. So the referenced page or the requested page is then loaded in that free frame. Now there are different techniques or algorithms for page replacement. We will be discussing all of them in the coming lectures. Now the question is, which page replacement algorithm works best, or which page replacement algorithm is more efficient than the others? So commonly, operating system evaluates the performance of different algorithms in order to determine which appropriate algorithm or technique should be adopted for page replacement. Generally, the performance is measured on the basis of number of page faults being generated by an algorithm. So, an algorithm is considered best which creates minimum number of page faults. As you all know, a page fault is a trap for operating system. An operating system leaves everything behind and searches out the required page. So operating system tries to avoid page faults, but it cannot be avoided completely. Even then, since there are too many algorithms for page replacement, operating system selects the one which will result in minimum number of page faults so that operating system cannot be trapped more often. But there is another issue. Some pages may be brought in memory several times. And this may happen if the protection bits associated with every page table entry is not updated time to time. So, if the protection bit is not associated with every page table or it is not being updated, so it may happen that some pages or one page may be brought in RAM more than one times. What this would do? It would not bring any benefit, but it would waste the memory. So an eye is kept on the arrival of new pages so that the protection bits associated with every page table entry is getting updated time to time in order to avoid one page making its entry several times. So this is how, if there is no free frame available in RAM, so operating system has to then perform page replacement. Page replacement is to select a page that is going to be swapped out to secondary storage and a new page is to be loaded at its place. Which page is generally selected as a victim to get swept out? Normally, a blocked page is swept out since block page is not running on CPU and it is in a waiting state. Suitable page replacement algorithm is selected to be executed to swap out a page and load the requested page. If the free frame is available, well and good, there would be no page fault. But if there can be page fault if even the free frame is available, but since the free frame is available, so the page replacement would not be executed, though there may happen page fault. But page replacement algorithm in itself takes some time to swap out one of the pages and swap in another page. So this is how the complete page fault mechanism is handled, either if the free frame is available or if it is not available. Next topic of discussion is page replacement. So we will see what is a page replacement and how different page replacement algorithm works. Page replacement is implemented very smartly by slight modifying the page fault service. Another bit is added with every entry of page table, and that bit is known as modify bit, also called as dirty bit, so that memory is not over allocated with same pages. A page that has been modified by the user, so its modify bit will be set to 1. Modified means updated or user made any change to the specific page. If a page has been modified by user, so only then it would be reloaded in memory. Otherwise, its previous version is enough to keep on working. A page is replaced to and from virtual memory as it acts as second RAM, having higher storage capacity than actual RAM. And you all know virtual memory is also known as logical memory. How page replacement works. First, when a page fault occurs, operating system finds the required page on secondary storage. Then operating system finds a free frame in RAM for the page to be loaded there. If it finds a free frame, the page gets loaded there. But if all the frames are occupied, then operating system activates the suitable page replacement algorithm to swap out a blocked page from RAM to disk, and the required page from disk is swapped into that frame. The page table entries of both the pages are updated. The one swapped out and the one swapped in. Swapped out page now has its valid invalid bit reset to 0, which was 1 before swapping, while the swapped in page had its valid invalid bit set to 1, which was 0 earlier. After doing that, the instruction that has referred this page gets restarted. This is how the page replacement procedure works. If free frame is not available, only then page replacement algorithm is activated. Operating system selects a victim page present in RAM that has to be swapped out in order to create a free frame for the coming page. The victim page is swapped out to secondary storage as shown in step 1, and its page table entry gets updated by resetting its valid-invalid bit to 0 as shown in step 2. The required page then is brought into RAM from secondary storage as shown in step 3, and its respective entry in page table is updated from 0 to 1 as shown in step 4. So an old page has been now replaced with the new one. That is all for now. We will continue our discussion on page replacement strategies and discuss different algorithms for page replacement in the next lecture. I thank you all.